So what I want to do today is, you might be actually watching the H.C. Verma classes on semiconductor physics. So I am trying to just basically give some explanation of the things that he passingly mentioned in his first class, for example. Okay, in this case, what I am planning to do is, in the first class, you can see that he talked about fusion. Okay, and when talking about fusion, he said that when two protons are colliding, they may not have enough energy to be able to come and hit each other. Before that, they will actually go back by repulsion. So, but how does the repulsion happen? So, during that time, he talked about energy of every proton is 3/2 into kb into t. And in his context, he may not be able to go and explain that, but because some people may be interested in knowing how this comes, I'll just explain that. Okay, I'll explain basically how energy of each proton, he has taken it as 3/2 into kb into t, where kb is called as Boltzmann constant. Okay, so I will start this with basically three things. One is what we call Boyle's law, second one is Charles' law, and third one is kinetic theory of gases. So Boyle's law is something most high school children are familiar with. So let's say you take a cycle pump, okay, and which also has an attached pressure reading. Okay, you connect it here to your bicycle and pump it till you get the amount of pressure that you want. Okay, so let's take this for an experiment, and we know we can actually calculate the volume of this. Okay, this is a cylinder. This height, if you take into the area of cross section, which is pi r square, will give you the volume, and the reading here gives you the pressure. So I am going to basically cap this and then do this experiment. Okay, I'll keep it at the top and take the volume reading. So I will say volume reading as V1. How did I do that? I just calculated it, the length and the area. So multiplied, I will get the volume reading. And I will also take the pressure reading. Okay. Now I slowly put the pump inside, let us say up to this point. Okay. Now what happened is that I actually now decrease the volume, and naturally the pressure gets increased here. I have capped it here. No? So when the pressure gets increased, I will now take the reading as V2 and P2. So I can take many such readings. As long as I am not doing it very fast and increasing the temperature inside, I always get the product V1 and into P1 and V2 into P2, V3 into P3, all of them are constant. So what really happens is, whenever I decrease the volume, pressure will increase, and when I increase the volume, pressure will decrease. So I would say basically the pressure is in a way inversely proportional to volume, or we can even write it as volume is inversely proportional to pressure. Okay, so this is basically called as Boyle's law. Only other statement we want to add is that at constant temperature, okay, the moment you increase the temperature or decrease the temperature, this law does not directly hold good, because temperature also affects the pressure of the gas, okay, inside. And similarly, let's go to Charles' law. Charles' law we can demonstrate using, let us say, a balloon. You take a balloon and blow it. Let us say it takes a spherical shape approximately, and one can actually calculate the volume. You can basically calculate and see the radius, or look at the diameter by radius by 2, and you get the radius, and you can do 4/3 pi r cube and get the volume. And then what you do is you get the volume V1, okay, and at room temperature. Let's say my room temperature is T1 is equal to some 27 degrees centigrade, or you can also call it as 300 Kelvin. So we have to write it in terms of Kelvin. So now if I actually put this whole thing into, let us say, ice cold water, I'll take an ice cold water in a dish and submerge this completely inside, okay, fully inside. ice cold water. Okay. And when it happens, keep it for some time, and then you measure the diameter, and from there measure the volume. So at V2, then measure, you will get a volume V2, and temperature at that time will be T2, which will be 273 Kelvin, because it is 0 degree. Okay. So you could do that at multiple temperature. Make sure that the balloon does not blast. It can go up to 30, 40, 45 degrees centigrade. It will not blast. Okay. So whenever you increase the temperature, the volume seems to go higher. Whenever you decrease the temperature, volume seems to go smaller. And in fact, if you actually dip this into liquid nitrogen, which is minus several degrees, so it will become very small, and it's very apparent to see that. The Charles law working there. Charles law simply says that the volume is directly proportional to the temperature, as temperature is measured in Kelvin. Okay. So decrease the temperature, volume decreases. So if you put these two together, okay, we could write it as V is proportional to T by P, or PV is equal to PV is proportional to T. So which basically can be written as PV is equal to some constant K into T. So experimentally one can determine these values. Okay. And if you look at a micro level, what this K is, okay, it depends on the number of molecules inside. Okay. And there is one more constant called Boltzmann constant which determines this. This K is supposed to be actually Boltzmann constant Kb into total number of molecules N. Okay. So if you put these two together, it will basically become PV is equal to Kb into N into T. Okay. This is one formula which comes out of Boyle's law and Charles law. And here also we have a one particular condition saying that these are all ideal gases. We will talk about what is the meaning of ideal gases when we come here into the kinetic theory. So this is on one side of the story. So let's go to the other side of the story, where kinetic theory of gases. There is a way you explain why pressure happens. Okay. So this pressure, you see, the pressure is here, and pressure we have defined in terms of volume and temperature, and a constant, and the number of molecules. So here you go here and say pressure is simply nothing but, the kinetic theory of gases says pressure is simply nothing but all these molecules which are there inside. Now they are supposed to be actually not staying at one point. They are randomly moving everywhere with random velocities. Okay. And they collide with each other, collide with the surfaces inside and everywhere. Okay. And these gas molecules, when they collide with the surface, or the cover, that actually gives us like a push onto that, and that push we call it as pressure. So there are billions of molecules. So when they go and hit the walls, that creates the pressure on the wall, and we are going to basically calculate that pressure based on each one of these molecules hitting that. So let's see whether that is possible. So that is what is kinetic theory. Okay. I will just assume now that there are many molecules. I don't care about them. They are moving in all directions. Okay. So I'll take one molecule, which is basically moving in a direction from left to right. We'll call it as X direction. Okay. And it is going and hitting the side wall. So if its velocity is, let us say, Vx, so I am taking it x because it is going in the x direction, and if its mass is, let us say, m, so what is its momentum? It's nothing but P, momentum is equal to m into Vx. So I think I will name momentum as some other number, letter, because P seems like pressure. Okay, I'll call it as momentum itself. So let me just erase it and write it down. Momentum of one molecule basically is equal to Vx into m. So now the pressure, how does the pressure come? So we want to basically do this. We want to calculate the pressure by using our simple formula. What is our simple formula? Pressure is nothing but force divided by area. So area we know. So if let us say you take a cube of one side dimension L and area is L square, so volume is L cube, that we know. Okay, let us say there are n number of molecules inside. That also we'll assume. Okay. So now pressure is equal to force by area. But force, how much is the force acting on this? So for that we will go with Newton's second law, which is basically a rate of change of momentum is force. So now if we calculate momentum and find its rate of change when it hits it, that is basically equated to force. So I will now say that change in momentum is equal to what? It is basically when it goes and hits and it comes back. Okay. Let's say it hits at velocity Vx and it also comes back with velocity Vx, but minus Vx because it is in the opposite direction. Why do we do that? That is one of the basic assumptions of the kinetic theory, saying that these molecules are fully elastic. When they are completely elastic, they come back with the same velocity. Okay. Now Vx into m is the momentum with which it is hitting, and minus Vx into m is what it is coming back. So we'll subtract one by the other and not worry too much about the sign of the total one, and we will get it as 2 into m into Vx. That is the change in momentum. So Vxm minus of minus Vxm, that is 2m Vx. That is for just one molecule. Now, how do we now calculate when the lots of molecules are bombarding? So whenever we talk about rate of change of momentum, the way we generally talk about at the macro level is if you go and hit something, okay, so the amount of time it took to change the momentum is basically our time. Okay, here what we do is that lot of molecules are going and hitting. Okay, so we will take all of them. All of them are causing the pressure. Okay, so in let us say small amount of time delta t, how many of them are hitting? That we will find out, and then we will divide it by delta t. That would give us basically the force. So what to do for that? How do we find out that? Let us say within, we talk about small amount of time delta t. Okay, so within that delta t, whichever was there at a distance, let us say certain distance, I will call it as some delta x. Okay, so within that delta x, whichever could hit, whichever could travel to that point, would hit it. Okay, so that is, let us say, if the velocity is Vx, this delta x definitely will be equal to Vx into delta t. Okay, so that is basically length. Distance is equal to velocity into time. Okay, so we got Vx into delta t. That is actually the distance. So that much distance, whatever is there, let me put a dotted line here, and which is there in that area, all of that volume are basically going and hitting. Okay, how many are there in that? So let us take the full volume and the density of the molecules. So if you multiply, number density, if you multiply, you will get the total number of molecules. Okay, so what is the full volume in that area? Volume of that area is delta x, that is the length here, and the area A. Okay, this is the total number of, this is the total volume. So volume is nothing but in that area delta x into A. Okay, how many molecules are in that? So let us say in the whole of this thing there are n molecules. Okay, whole volume is, let us say, capital B. Okay, so now volume density or a number density, what we call number density, is equal to total molecules divided by total volume. Okay, So that into this volume will give you total number of molecules here. So now our molecules that we are considering are Px into delta T, that is our delta X, okay, into A, okay, into N by V. So totally this many basically molecules are going to hit. Understood? So this is little tricky. Just understand this. How do we get this volume, small volume, and then how do we get the number density by total number, and then multiplying the density into volume will give number of molecules in that area. Okay, so that is what I have done. So this is number of molecules in the small area. Okay, small volume. So now what will happen to the total change in momentum? So change in momentum now is equal to, so total basically is equal to this number of molecules into change in momentum per molecule. This is per molecule. So that I will write it as 2 into m into Vx square, because 1 Vx is here, okay, into delta T into A into N by V. This is volume. Okay. So now total change in momentum divided by delta T is the force. F is equal to change in momentum divided by delta T. So if I put that here, so this delta T will go 2m into Vx square into A into N by capital. Okay. So now if I want pressure, which is nothing but F by A, so how do I get that? So I will just remove the F from here, A from here. Okay, so which will become 2m Vx square into N by V, or PV, if we bring it this side, PV is equal to 2 small m into capital N into Vx square. Okay, now you see, okay, so the thing is that this PV is equal to 2m n into Vx square, we made some very rough assumption. So all those molecules which were here actually are all going in this direction, okay, which is not really right. Okay. Some of them may be going in the opposite direction. Some of them may be going up, some of them may be going down. Okay. So we will basically take it as all 6 directions. Okay, and we will now remove the Vx and say V. They can be having any velocity. Okay, so then we can simply say real velocity PV is equal to this divided by 6. That divided by 6 is simply nothing but 1 by 3 mn into. So I am going to now here write V square and put a dash on the top of it. What does it mean? Because I have made so many assumptions. All of them are going in Vx. That is also not true. So we are going to take an average of V square. So some of them may be going slowly, some of them may be going fast, and many such things. So on an average, this is the V in any direction. So we will take an average. Okay. And another important thing that we need to understand here is that we are neglecting at this point all those collisions which are happening inside. Okay, so that also can be justified by several other assumptions. So I will not get into the detail of that. But however, PV is equal to 1 by 3 mn capital Mn V square is our PV we got. So you now see there are two different equations for PV, and these two are going to give us finally whatever we want. Okay. To be able to show that, I will erase this Charles law, Weiss law part. Okay, and I will tell you. Okay. So there are two things. I will equate them. Whenever there are two equations which are left hand side are equal, I will just equate them, which is Kb into N into T is equal to 1 by 3 into M into capital N into V square, an average V square. Okay. So it is the average of V square, not average of V and N square. So that is why we write it like that. Okay. So now N gets cancelled. Okay. Now 1 by 3 mv square, I will write it as actually, okay, 2 by 3, okay, then half mv square. So this 2 gets cancelled, is 1 by 3 mv square only. On right side I will get kb into t, because n got cancelled anyway. So here, this part, now we can call it as energy. So all is kinetic energy. There is no potential energy inside that. Okay, they are so small, and we are not taking gravitational pull, everything into consideration there. Okay, there is no attraction between them. There is no electrical attraction between them because they are so far away from each other when compared to their sizes. Okay, so we will say only kinetic energy it has. There is no potential energy. So this is nothing but our kinetic energy E. Okay, so 2 by 3 E is equal to kb into t, or E is equal to 3 by 2 kb into t. So this is basically what we wanted to prove. And in that video, this was basically assumed that this many things are known to you already. Okay. So if you have any kind of a doubts, you can ask me, or you can put a note below. Okay, I will try to answer. Thank you very much.